About the capacitance of a capacitor. See, first we'll move on to what is capacitance. See, let us suppose we have a sphere over here having radius r, which has charge q on it. So basically capacitance is the ratio of charge to the potential. And the unit of capacitance is what? Farad. And charge is what? Coulomb. And potential is measured in volt. So when we place, we know that potential of this sphere will be equal to what? Kq upon R, and capacitance of this charge sphere will be equal to what? C is equal to Q by V. V is we have Q. This is what? K, Q, R. This get cancelled out. K is what? 1 by 4 pi epsilon naught, which can be written as 4 pi epsilon naught into R. It's clear? See what we have? Capacitance is what? It is equivalent to charge upon potential. And capacitance of a capacitor is said to be 1 farad if a charge of 1 coulomb increases the potential by 1 volt. We are calculating over here the capacitance of uniformly charged hollow sphere. This is capacitance of uniformly charged hollow sphere. So it is coming out to be what? 4 pi epsilon naught into R. Capacitance of a hollow sphere. Uniformly charged hollow sphere is 4 pi epsilon into R. R is basically the radius of the sphere. Next we will calculate the capacitance of a parallel plate capacitor. Capacitance of parallel plate capacitor. See what we have. See, let us suppose this is the plate we have. C is equivalent to what? Q by P. What is potential between these plates? Potential is basically electric field into D. Electric field in parallel plate is what? Sigma upon epsilon naught into D. Sigma is what? Surface charge density. So what we have? Sigma can be written as Q by A epsilon naught into D. What do we have? C is equivalent to Q into D into A epsilon naught. Q get cancelled out. We are left with A epsilon naught upon D. This is capacitance of a parallel plate capacitor. D is basically the distance between the plate, and A is area of the plate. Now we will calculate the capacitance of the capacitor when we are connected in a series and parallel. So let us suppose it has capacitance C1, this is C2, this is C3. Let us suppose it is connected to potential V. See what will happen? This charge will be constant throughout this, and potential over here will be V1, V2, V3. Total potential is coming out to be V1 plus V2 plus V3. What do we have? This is, we know that C is equal to Q by V. V can be written as Q upon C. This is Q upon C1. This is Q upon C2. This is Q upon C3. So what we have? 1 by C is equivalent to 1 by C1 plus 1 by C2 plus 1 by C3. See, in case of capacitance which is connected in series, what we have? We have charge is constant. Same charge follows through all the capacitors. But suppose when they are connected in parallel, what will happen? See, when they are connected in parallel, they will have different charges will go through them. This is capacitor C1, this is capacitor C2, this is capacitor C3. What will happen? There is distribution of charge Q1 plus Q2 plus Q3. Potential along all this capacitor will be equivalent to V. What we have? This is C into V, this is C1 into V, this is C2 into V, C3 into V. In parallel combination, what we have? Potential across AB will be same. Potential is constant. So what will happen? This V will get cancelled out. Then CP will be equivalent to C1 plus C2 plus C3. Now we'll go for energy stored in a capacitor. See, energy stored in a capacitor is what? See, it can be half CV square, it could be half Q into V.